Well, let's talk about belt friction. So last time we talked about square threaded screws. And so now we're going to talk about belt friction. And of all the different types of friction, it's 4 different types that we're dealing with. This is the only one where I'm not going to do the derivation, and you don't have to worry about the derivation. The other ones, I want you to understand how to come up with this stuff. So this is the only one of the 4 where you don't have to derive it. And the idea of belt friction is this. So this is like a castle. Here's Rapunzel. And for the prince to come, climb up, visit her, he climbs up her hair. Okay, she has like super long hair, and he climbs up the hair. And that would hurt a lot. So what she does is there's a pole, and instead of just hanging her hair down, you can see how well it's working because she's happy. She wraps her hair a bunch of times around this pole, and then it goes down. And then the prince can I'm just going to be drawing this prince for the rest of the time. So then the prince can climb up the hair. Okay, wrapping the hair around the pole doesn't change the force that the prince applies to the one end. It doesn't change the force applied to the end of the hair by the prince. But the friction with the pole takes some of the required force for equilibrium away from her head. So the friction, this belt friction, takes up some of the force required for equilibrium. So there's less force on Rapunzel's head. That's the idea. And if you have, so if this is a circular cross-section of, like, this would be a cross-section of that pole in this instance. And say that you have a cable of some kind leaving here, and a cable of some kind leave, well, the same cable, but kind of cable leaving there. And this is the center. Then figure out the angle between the two places where the cable leaves that center line, and that angle is beta. Beta has to be in radians. So let's say that this is T1 and this is T2. And T1 is greater than T2. Right. So T2 over T1 equal to E to the power of the coefficient of friction times that angle beta. So this is the coefficient of friction. If this cable is at rest relative to that pole or whatever it is, then we're talking about static friction. If the cable is sliding along that, like maybe it's a pulley, but the pulley, the cable is actually sliding along the pulley, then that's the coefficient of kinetic friction. Is that positive? I'm sorry, I did this backwards. So T2 is the force that you're trying to support. Okay, so let's see how this works. So let's say that there's a pulley attached to the, well, it's not a pulley because it doesn't rotate, but so let's say this thing is fixed, and we have a cable leaving on one side and supporting a 100 kilogram mass. And on the other side, we want to figure out what the force is that's required to hold this up. We'll say that the coefficient of static friction is 0.4. So what force is required for equilibrium? First, if the cable, doesn't go a full time around, it just loops over the top of this So if the cable only touches the top half of that cylinder, and second, what if that cable goes over, wrapped around, and back? So 3 full lines around, and then down. So 3 full times around the cylinder.
We're assuming the cable's in contact with
Right. That's right. Yep. And you have to figure out which one of these two is T1 and T2. The idea is always that whatever you're trying to support is the bigger force, because the reason that we have it wrapped around the cylinder is to try to make the supporting force less. Okay, so the force, so what we have is a force here that's equal to the weight, 981. And then over here is our T1 that we're trying to find. And let me talk about that for a second again. So you would get this wrong if you treated this like it was the force T2. And so, like, is there a way to always be clear about which one is T1 and T2? And the idea is any kind of friction opposes motion. Okay, and we're trying to use the friction to support whatever we're trying to. So we're trying to support this weight. We're trying to support this force of 981. Okay, if the friction wasn't there, this would slide this way, and so the friction has to act in the direction of this force, and so this force is going to be something smaller than this. Okay, so you need to think about what's the thing that we're trying to support, and the force you're going to calculate is going to be less than that. Well, I suppose sometimes you could do those problems backwards, but you can think about it in terms of which way the friction acts. Which way do you want the friction to act to be taking advantage of it? Okay, so for part A, all we need to know is the coefficient of friction, which we have, and that angle beta. What's the angle beta here? Yeah, beta is I, because it's this. The coefficient of friction is 0.4. And so 981 over T1 is equal to E to the power of 0.4 times pi. And so T1 is equal to 981 times e to the power of 0.4 pi. And what do you get for that? Divided by? Yes. (981) times e to the, negative 4. Okay, what do you get for that? Okay, so T1 is equal to 279.2 newtons. Okay, so that's pretty useful. It cut the required force down quite a bit. When we wrap it around 3 full times, we expect that force to be cut down even more, because the more times you wrap it around, the more friction force you're building up. And so for part B, so now it's going to go, so starting here, where this cable touches the side, it's going to go 3 full times around. So 2 pi, 4 pi, 6 pi, and then it's going to go over the top 1 more pi to get to the exit point. So beta is 7 pi. Who's with me on that? Okay, so beta is 7 pi. We still have the same coefficient of friction. So 981 over T1 is equal to E to the 2.8 pi. And so T1 is equal to 981 times E to the negative 2.8 pi. And what do you get for that? 0.148 newtons. So that's you never get down to 0 by this calculation, but you're basically not requiring any force anymore. Friction is taking pretty much all of it. Yes. Oh. Yep. That's right. Yeah, it's a limit, right? Yep. Yeah, both of those two. Yeah, I mean, those are always finite, and so I mean, I guess if you. So this formula says another way to write it is T1 is equal to T2 times E to the negative pi. Negative mu beta, I guess. And so these are always finite. This is equal to 0 at e to the negative infinity, like as this approaches e to the negative infinity. So for any, these are both positive, but for any finite values of these, you get some positive number. But it just gets smaller. Yep.
So is there a way to tell like height on those correlations? Or is it
Yes, let's see. I don't remember the derivation enough to, but the derivation is what would tell you that assumption. I'm thinking that that it does not make any distinction between the top and the bottom. So that friction is just, well, that, well, the cable, let's not go there. Okay. But I don't think it makes a distinction, but it does, the cable tension does change as you go along the cable, and so I think that the friction at each point is determined by the tension in that part of the cable. So whenever you see an exponential relationship between variables like this in engineering and physics, it usually comes from a differential equation, and I think that's where this came from here. Uh, was there another question? Yeah.
If you like accidentally met T1 and T2 in the beginning, is the answer you get like
It goes the other way. Yeah, you get something bigger than 981. And so you have to think about what you want to have happen. Okay. So like in this case, we're trying to rig this up so that that T1 is smaller than 981. And so you can just work it out so that you come up with a smaller value. But yeah, so it's sort of like, it can be confusing, like, well, so wait, I can switch these, and then I get something here that was maybe like 1200, say, or something, bigger than 981. And it's still right. So what would be happening there? Well, what would be happening there is now if you apply a bigger force to this side, then without the friction, the thing would accelerate this way. So the direction of that friction force switches. You know what I mean? And so you just have to think about which of those two forces you want to be smaller and rig it up that way.
you solved it with the
Yes, that's right. Yep. And it would be something bigger than 981. Yep. Okay. That's all I want to say about belt friction. So let's talk about bearing friction. Bearing friction. And there's two kinds of bearing friction. Journal bearings and thrust bearings. So I'm going to start with journal bearings. And this is what it looks like. So you have this shaft that is rotating in a hole in this bearing. And so it goes through the middle like this. And as it rotates, this part of the shaft is in contact with the bearing. And there's friction there that acts in the opposite direction that this shaft is rotating. Or if it's static friction, opposite to the direction that this shaft would rotate if the friction wasn't there. And so we want to calculate how big that friction is. So let's imagine, so here's how we're going to visualize it. So imagine looking at it from this side. Okay. And Let's think of a free body diagram of the shaft. And we're looking at it from the left. You know, from the left side in the figure above. Okay, so there's the shaft, and here's the center of the shaft. And it's rotating this way. There was no friction if you integrated all of the contact forces between the bearing and this shaft. You could represent it as a single point force. Okay, it's really a distributed load that's distributed all the way around, but you could represent it as a point force, just like we always do for calculations. And that point force would be a normal force right on the bottom pointing straight in. That's if there was no friction. Okay, and so then, and this thing would just spin, you know, forever. But there is friction. And that friction has to fight this rotation. So if it's spinning this way, the friction has to be causing a moment in the other direction. Okay, so that friction produces a moment in the opposite direction of the rotation. And what happens when so how does that work? There is a downward force acting like this that's equal to, you know, the weight, whatever force is pushing the bearing and the axle together. Okay. If there was no friction, there would be an equal and opposite force pushing up straight on the bottom. And those would counteract each other. And you get equilibrium, and this thing would just spin at a constant angular velocity. Well, we know that if it stays in equilibrium, there has to be an equal and opposite force. Like there still has to be a force up with a magnitude of W. But we know that that force has to produce a moment. Okay, and so in order for this equal and opposite force W to produce a moment that's in this opposite direction, that friction has to shift it over to the side. Okay, so if you integrated all of this distributed load contact force and found the point force that represented it, it would be a force with a magnitude W but shifted from the center line. Okay, so you would have something like this. And this is shifted. You can think of this as being shifted by some angle. If there was no friction, this theta would be equal to 0. But friction causes that angle to develop. And we can break this this force up into what we know are the two components, the normal force and the friction force. So we know that a normal force is perpendicular to the surface. And we know that the friction force is parallel to the surface. These two are perpendicular. And what's the magnitude of that friction force? Yep, that's right. That's mu times the normal. Okay, so now we know a lot about this angle. If you think about it, this angle theta has to match the angle of this right triangle here. So we know a lot about that angle theta. If we know what the mu is, we can do the trigonometry and figure out, we could come up with that angle in degrees. But what do we want to use that angle for? What are we trying to find? So we know the magnitude of this force W. That's something given in the problem. That just depends on how much weight is. But we need to know what the moment arm is to figure out the moment that this friction is producing. Okay. You with me on that? So we're trying to figure out this distance from here to here. I'm going to call that rho. And this is what we want to find. So I'm calling that rho because that's the moment arm. So we want to find that rho because the moment produced by the friction is W times rho. Well, we have these two triangles. We know everything about this one. If we could come up with the length of this hypotenuse, now that we know this angle, we can figure out what rho is. And the length of this hypotenuse is just the radius of the axle. So that's something we can just measure. So this is R. And so that the moment produced by the friction is equal to W rho, which is equal to W, that rho is R times the sine of theta. And we could come up with a formula for all this, but I think if you just get it to, this is the best way to think about it. Just think about it this way, and you can solve for that theta, and then plug these numbers in. So what about the coefficient of friction? How does that come into this? That doesn't show up in that final formula. Where does that come in? It comes in calculating theta. Yeah. So if you have a very small friction, that theta is going to be very small. You know, if you have zero theta, zero mu, no friction, then that theta is going to be zero. So let's do information. So let's say we want to keep this axle rotating. And let's say that there's a downward force of 4,000 newtons on each side. And let's say that the radius of this axle is 6 centimeters. I guess that's the diameter, the way I drew it. So the radius is equal to 3 centimeters. And let's say that the coefficient of static friction is 0.05, and the coefficient of kinetic friction is 0.02. So what's the external moment required to, first of all, initiate motion, and second, to maintain motion with a constant angular velocity? So before I go into this, just intuitively, what's that M? What am I talking about with that M? So if you had perfectly efficient axles and no friction of any kind, once you got your car up to speed, you could just turn the engine off, and just coast. But there's a bunch of kinds of friction, but one of those kinds of friction is this bearing friction. And because of that bearing friction, your engine has to apply a moment to that axle to keep it rotating. Okay? And so that's what we're talking about. What's that moment M that, like, the engine or whatever is powering this thing needs to apply to that axle to keep it from slowing down or to make it start moving? Okay, so free body diagram of the axle. Do you know what this is? Axle rows? Okay, you don't need to draw that. Okay, so we know we're going to be applying this moment M. That's what we're trying to find, the moment M that we need to overcome this, the moment produced by the friction. The friction has to apply an opposite moment to that, and to apply a moment in that opposite direction, the weight force that's applied here needs to be counteracted by a force that's shifted in this direction. Okay. If we were talking about the moment going the other way, then this weight force would have to be shifted over. It needs to be shifted in the direction that produces the moment that counteracts that one. What's W? 8,000. We're doing a free body diagram of the whole axle. Okay, so this is 8,000 newtons. And so there's an upward force produced by the bearing that's also 8,000. And so we want this angle theta. Eventually we want to calculate this distance. And so this is broken up into a normal force and a friction force. For part A, we're looking to initiate motion. So this thing is currently at rest. And so this friction force is going to be the coefficient of static friction times the normal. So this is 0.05 N. This is a right angle. This is the angle theta. So let's think about that triangle. This hypotenuse is 8,000. This is N. This is 0.05 N. And this is theta. So SOHCAHTOA says the tangent of theta is equal to 0.05 N divided by N, or 0.05. So that theta has to be equal to the inverse tangent of 0.05. And you can do that in radians or degrees. We're just trying to get that angle. So what's theta equal to? What? 2.26? 2.86. No, that's fine. Okay, so 2.86 degrees. The radius of the axle is this, and that's 0.03. So the row vector that we want is 0.03 times the sine of 2.86. And what do you get for that? 0.0015. That's in meters. So that's 1.5 millimeters. So we're not talking about, it's the way I'm drawing it, that big angle is very exaggerated for those small friction values. And if you have a journal bearing and an axle, you're expecting this thing to roll sometimes, so you want to have low friction. But I'll talk about that again in a second. But so this is our moment arm, and so then the moment produced by the friction is 8,000 times 0.0015, and what do you get for that? What? 12 Newton meters. Now that's what that's really saying is that's the maximum moment that static friction can apply before you exceed the limit and you start to move. But this is also, that means that's also the external moment you have to apply to get it to move. To initiate motion. Okay, so now part B. Now we want to do basically the exact same thing, but now we're talking about it already moving, and we just want to know the moment that we need to exert to keep it moving. Okay, without any angular acceleration. Do you think that moment's going to be bigger or smaller than the one we just calculated? It is going to be smaller, and why do you think that is? The coefficient of friction is, yep, exactly. The coefficient of friction is less when it's moving. And mathematically, that means that angle theta is going to be smaller. And if that angle theta is smaller, then that moment arm is smaller. Seems kind of unnecessary to do this all again, but I'm going to go through it again because this is what you need to do in these problems. Okay, so this is 0.03. This angle is theta. And this is the row vector that we're trying to find. And, whoops, I did that the wrong way. This is the 8,000 Newton force that's counteracting this 8,000 Newton force. This angle is theta. No. That 8,000 Newton force is the sum of a friction force and a normal force. So this is the normal force pointing perpendicularly towards the surface. This is the friction force, and now that we're talking about kinetic friction, this is 0.02 N. That's right angle. So over here we have 0.02 times the normal. Here we have the normal. And so theta is equal to the inverse tangent of 0.02 N over N. And the N's cancel. And what do you get for theta here? 1.15 degrees. And so the row vector is 0.03 times the sine of 1.15 degrees. And what do you get for that? 6.0 negative fourth. Okay, and that's meters. And so the moment is equal to 8,000 times that. which I think is just 4.8. And so in order to start this axle moving with those loads applied to it, you have to apply 12 Newton meters of torque to it. Once it's moving and you're at the speed that you want to stay at, you only have to apply 4.8 Newton meters to keep it in equilibrium, keep it from angular acceleration. But now I'm going to tell you something that's a little sad about this. So notice all of these friction calculations are assuming that the force of friction is equal to the coefficient times the normal force. We've used that in every one of these derivations, and that only applies for dry friction. And so if you have an axle that's totally surrounded by oil or something, that's not dry friction. You can't use this for any calculations where fluid dynamics behavior dominates what's happening. So this doesn't work for oil. It does work for like dry lubrication, so in some applications you might use that. So like a graphite lube or something, it would work for that. But you can't use this with oil. The lubrication of oil depends on other things besides, it doesn't satisfy that equation. Any questions about that? It's not because of that, although that's another thing you have to deal with. But it's because what viscosity does is cause a drag dependence on the speed of rotation, and so if you're going to take into account the fluid dynamics effects, you'd have different answers for different speeds. If you're dealing with dry friction, no matter what speed it's going, if you want to keep it at that speed, the moment you have to apply is 4.8 Newton meters. Obviously, that's still leaving out some things like rolling resistance and air friction and whatever, but this is the friction from the axle, or, from the bearing to the axle. Any other questions about this? Okay, well, let's do the quiz, and then Tuesday I'll talk about the last thing, and then, yes? Yes, we're going to use this same F equals mu normal for thrust bearings, and so, yeah, everything.